All right, welcome everyone to this Monash Cybersecurity Seminar. So today we are happy to welcome Lena Horlemann. And Lena received her PhD degree in mathematics from the University of Zurich in Switzerland in 2013. Then she spent 1.5 years as a research fellow at the Department of Electrical and Electronic Engineering at the University of Melbourne and at the Department of Electrical and Computer Systems Engineering at Monash University in Australia. Then she was a postdoctoral fellow at the EPF Lausanne, Switzerland from 2015 to 2017, after which she was an assistant professor for mathematics and information technology at the University of St. Gallen in Switzerland. And then she recently joined School of Computer Science as an associate professor at the same university. And today she will talk about code-based cryptography with restricted errors. Thank you, Lena. And the scene is yours.
Thank you for the nice introduction and the invitation. All right, so maybe as a quick, further intro. So my background is more in coding theory than in crypto, but as many of us do, we also like code-based cryptography as a coding theorist. So there is my intersection to cybersecurity, basically. So, all work I've done in cryptography or cybersecurity is mainly code-based. And so is this work. So most of the language I use is coding theory-based, but you don't really need much background in coding theory. I think everything I'll explain is just linear algebra in the end. So okay, so I'll try to more or less explain the little details that might not be known to the non-code-based cryptographers among you. Okay, so and of course let me give credit to the people who should get it, so who deserve it. So this is joint work with all my Italian-speaking friends here, so Marco Baldi, Massimo Battaglioni, Franco Chiaraluce, Edoardo Persichetti, Paolo Santini, and Violetta Vega. So let's see. Well, probably for you don't really need an explanation why post-quantum cryptography is important, but anyway, for completeness, let's start with that. So most of public key crypto systems that we have in use these days are either based on one of these three problems: integer factorization, discrete logarithm in any version, including the elliptic curve version. And we do know since ages ago, so since 1994 latest, that these problems are not hard enough anymore once we have large-scale quantum computers because of Shor's algorithm that is able to solve these mathematical problems in polynomial time on a quantum computer. Hence, since we are currently building quantum computers and they are getting larger and larger, so at some point in the future, not too distant, let's say, we will have quantum computers that will be a threat to the cybersecurity aspect of all these asymmetric crypto systems if they're based on one of these problems. Hence, we need new crypto systems. And this is what we study in post-quantum cryptography. Okay, and I mean, this is, from an applied point of view, really more stressed in particular by this NIST competition that some of you have taken part in yourself. So I guess, again, don't have to spend too much time on that. The main streams, not a complete list, I have to say, but the main streams in post-quantum cryptography are code-based, lattice-based, hash-based, multivariate, and supersingular elliptic curve isogeny cryptography. We'll focus on code-based in this talk here. In code-based cryptography, there are two standard and classical crypto systems that everyone kind of builds on. So these are called the McAleese and the Niederreiter crypto system. They are kind of cool in the sense that one uses a generator matrix, the other one uses a parity check matrix. But again, if you're not too familiar with coding theory, it doesn't matter. More or less what is important is that they're equivalent from a security point of view. You can reduce one into the other. And from an implementation point of view, usually Niederreiter is the preferred one because it's mostly a little bit faster in implementations. The original McAleese proposal uses binary GOPA codes, and just a family of codes, and has been unbroken for 30 years. So that's one of the nice things here. This original proposal has been around for more than 3 decades by now and unbroken. So that really makes us believe that this is a very secure idea that we're talking about here. The overall advantage of code-based crypto systems is that they're fast. Computations are usually very fast compared to other options. The disadvantage is that the public key size is usually a lot larger than in other systems. And that's then hence the main focus of current research. We're trying to reduce the public key size when we're talking about a normal encryption, decryption, asymmetric coding crypto system here. Now today we'll talk about signature schemes in the end. And signature schemes have been a bit tricky for code-based crypto. So it's taken quite a while to come up with the first signature scheme at all. That was done in 2001. There are various problems with that system still. Other variants, of course, have come up, have been broken, and so on and so on. A more recent and more promising approach is the wave signature scheme here from 2019. And then there is a whole family of digital signatures that are created from a zero-knowledge identification scheme via the well-known Fiat-Shamir transform. So from any zero-knowledge identification scheme, you can create a digital signature. And there are several code-based zero-knowledge identification schemes that work. And of course, again, they come with advantages and disadvantages, which we'll talk about in this talk as well. So we'll look at this scheme here. We'll create a variant of this, what I call the CVE, zero knowledge identification scheme, and simply get some new coding theoretic ideas in there that improves the parameters in the end. So the main idea of code-based identification schemes is as follows. The main security idea in any part of code-based cryptography is that decoding a random linear code is a hard problem. And again, if you don't really know what that means, doesn't matter. I'll explain how we use this problem in our systems in the following. So the public information, or the public key, is the parity check matrix of a random linear code and a syndrome. And the secret is the solution to the corresponding syndrome decoding problem. And the prover in this identification scheme wants to prove that he or she knows that secret, and the verifier wants to be able to verify that. Okay, so what is that syndrome decoding equation? So really, if you don't know what a parity check matrix is and so on, there's not much magic in there. Just think of a random matrix of, well, doesn't even matter, some given size, usually we say R by N. Then an error vector. So this is your secret. This is what you choose, and you want to prove that you have knowledge about. So this is, in most cases, a low weight vector. So low weight meaning low support, okay, low number of non-zero entries. And the syndrome is just the solution to this equation. Okay, so this error vector times that parity check matrix gives you another vector, and this is what we call the syndrome. So you are given as public information the syndrome and the parity check matrix and the weight of E, but the secret itself, so that actual vector E, that is the secret, and finding that is proven to be an NP-hard problem. Okay, if you're thinking about a random matrix here, and you have knowledge about this, and just the weight of this E, finding that E is a hard problem, and that is the security idea of, well, everything in code-based cryptography. Okay. And in this case of, well, keeping the secret. Here's the original. Yes, please.
Am I welcome to ask questions?
Absolutely, yes.
How hard is this decoding problem in terms of R and N? Like how large should they be to achieve some sort of?
I don't know the numbers by heart, but I mean, I give you a table in the end, what we need for 128 bits security. It's, what are they in practice? I have to check at the end.
And what about asymptotically splitting?
What exactly do you want to do asymptotically?
Like, what's the best known attack to this problem? What's the best known algorithm that can solve this problem? Is it sub-exponential? Is it exponential? Is it
exponential? They're all exponential. I mean, except, so now it really depends on what you prescribe on your error vector. Okay, so if you generally say, I mean, this NP proof is really for the general family, saying, you know, we take a random age and we simply say we fix the weight of the error vector. So we basically choose E uniformly random from the set of all vectors that have a prescribed Hamming weight or number of non-zero entries. Then you do the whole proof. But now, of course, you can do different restrictions on your error vector. This is basically the idea that we present in this paper. Instead of just saying, well, we're fixing the support size or this Hamming weight, we can also say, you know, it needs to have this requirement or this, you know, property, if you like. You simply prescribe a set that you choose your error vector from. And then it depends a little bit. So in general, you would say information set decoders are the fastest generic decoding algorithms for the normal low weight Hamming syndrome decoding problem. These are exponential in all parameters that you want to think of. Then if you do some other restrictions on the error vector or you change your alphabet or whatever, there are specific versions that you might not call information set decoders anymore. They're still exponential. Except, I mean, if you do a really stupid restriction on your error vectors, you might get into something that's not exponential anymore. And then of course it's not interesting for cryptography. But
and
if you're really
it doesn't really matter if you choose H like with a little bit of a structure, not completely a structure.
No, it might matter.
Yeah,
it might matter. Yeah, and that is for, you know, for the main research stream, I would say, that most people work on for really the normal asymmetric crypto systems, public key crypto systems. That is exactly what people try to find structures on H where it doesn't make it easier, the problem. However, you can then use it to, you know, reduce the size of representing that H or so on.
Yeah, and by structure, I mean just having like regular codes here, like fixed number of ones or non-zero elements in one row or columns.
Exactly. All of that could make a difference, and there's no general answer to that. Of course, I mean, I can give you kind of like from a coding theoretic point of view, I can give you a very easy answer. If you take a structured code like a Reed-Solomon code, then the whole decoding problem becomes not even cubic in polynomial time in solving it. So of course, you know, I mean, there are all kinds of extremes from, let's say, quadratic solving time to, well, exponential if there's no structure. So
but what is it about binary GUPA codes which makes it hard?
That is also
that's
a question that
algebraic,
people have thought about for 30 years now. What is it about that makes it so secure? Usually the answer is it's right in the middle between having a little bit of structure but not too much.
Okay.
Yeah.
All right.
All right. So let's have a look at this identification scheme that we want to look at. So the public data is this matrix H that we have, the public, the parity check matrix. Then of course, or I mean, Q is the field size, N is the length of the code, K is the dimension of the code, W is the weight that we prescribe. So this is now the original CVE scheme, which we are gonna tweak a little bit then later on, but this is the original version. So then your private key is some error vector E, so some vector E of length N over FQ with a prescribed weight W. Okay, so this is just the notation for the Hamming sphere. That's the H for Hamming, S for sphere. Okay, but this is really just all the vectors in FQ to the N of weight W. And the public key is the syndrome. All right, so you can compute when you set up the system, you have your secret E, your public H, you compute this S. but of course you're not revealing E, okay? Yeah, so that's the public key. And now the verifier wants to check that you actually do know this E, which fulfills both this equation, the syndrome equation, and that it has the correct weight. So these are the two properties that are important here. Now, what you do in the actual identification scheme is the following. So what is all of that? So we're choosing this $sign as we're choosing uniformly at random some vector u from fk to the n, and this is the set of monomial matrices, so permutation or scalar multiplication of any of the coordinates. All right, so these are the monomial matrices here. So we're choosing one of those as well, call it tau, and we're computing these two things, okay? The two commitments, we call them. The hash of this monomial matrix and this random u times parity check matrix, and then well, these two guys here, we hash them, and we send those two to the verifier. The verifier now chooses randomly a non-zero element from FQ, sends it back. The prover now computes this guy here. Okay, so this is the actual secret. Here we use the secret. That's the Z that came from over here. Well, you simply compute this thing, send this back, and the verifier chooses again one of these two binary values, and depending on which of those the verifier chose, the prover has to reveal either that monomial matrix itself, or the monomial matrix acted on the error vector itself. So what does that mean? It's really just a permutation of the error vector, and possibly the non-zero values were multiplied by some element from FQ. All right, and well, then the verifier accepts in the case that here he chose b equal to 0. If he can recompute a bunch of stuff, compare it to that first original commitment. If that is correct, they accept. And in the other case, you compute this other thing. Okay, so many details you can look up in detail if you have time. But what is important is basically what you're proving here as the prover is that E that you have knowledge of fulfills the syndrome equation. That's basically what you recompute here, without revealing any information about E, okay? And in the second case, you're revealing, you're proving, you're not revealing, you're proving that that secret that you have knowledge of has the right weight. Okay, so that's this part here. And then of course you have to repeat this scheme over and over and over again to then at some point really prove to the verifier that you have knowledge of both. Okay, that's the idea here.
I've got a question.
Yeah. Sure.
So this tau, you in case B is sent, you are revealing E prime, which is tau of E, right? And you said it's
exactly.
just a permutation of E, right?
Yeah. Plus, so if you're not in the binary, it can also scale all the non-zero elements. So what the idea is here from a security point of view, so if you're now changing this, which is the idea that we're doing, you're changing this set where you can choose your error vector from,
yeah,
then you have to choose these maps accordingly, because the idea is that this map is transitive on that whole set that you chose your E from. So basically it just maps your E to any other vector by the same probability from that set.
Yeah, so E,
or the Hamming weight,
E prime is also belong to the S.
Exactly. So okay. You're not revealing any new information.
Yeah.
It's just any other element from that set.
Yeah. And S is large.
S has to be large, exactly. Yeah.
Yeah, okay.
Yeah, that's the idea, right? So if you, of course, as soon as you had knowledge of both tau and E prime, I mean, you could solve everything and get E. But if you only know the result E prime without knowing tau, you haven't gained anything. It's just uniformly distributed over the whole sphere that you chose your E from some other element.
Okay.
Yeah. That's the idea. And well, the other thing, maybe since we're talking about it now, the other thing that's important about these maps here is that it's linear, because otherwise this computation here wouldn't recover exactly that UH, and I mean, it has to match, these two guys have to match, right? So that's basically what you have to fulfill here as well. So these are the two things that you want. You want these maps to completely hide the information of E. So it has to be, you know, exactly a map that can map your E to any other element of the set that you chose E from, and it has to be linear. And that we'll see that that might be a problem in the first idea that we had. So just from a theoretical crypto point of view, you can prove that this is a proper zero knowledge identification scheme. Okay, so it's complete, i.e. an honest prover always gets accepted. I mean, that's good. Otherwise, yeah. I mean, that's really the first thing you really want to have, right? So then the zero knowledge part, that's always a bit tricky to prove, but it really is kind of with, you know, that idea that I was just trying to explain. You don't, the prover or, no, sorry, the verifier or any outside observer doesn't gain any information about your secret E from any of the communication that you send back and forth. And it's sound in the sense that an impersonator only has a very small probability of getting accepted. And actually, if you only do one round, the probability is not even that small. It's actually Q divided by 2Q minus 1. All right, so depending on your Q, it's larger than 1/2. And if your Q goes to infinity, then it becomes equal to 1/2. So that, I mean, it's not even that small of a probability. However, as I said, you have to repeat this protocol over and over. And then, of course, you can get to, I mean, 1/2 to the number of rounds. And then, of course, you can get this very small. So that's definitely something that you want to and have to do. Now, for one other thing that is important for this cheating probability is how likely is it that you can solve the syndrome equation? And hence, how likely is it that maybe this equation has more than one solution? So you don't want more than one solution. You really just want one solution. Otherwise, it makes it easier for someone to just by chance find a solution to that. And that is really something that comes from coding theory again. And for random code, what we use there is called the Gilbert-Bashamov bound. So that tells us by very, very high probability, you get that a random code achieves this type of minimum distance. And hence, then it gives you the exact weight that you should choose for your E such that there's only one solution. So we do that. The security level depends on the fastest generic decoder, what I was asking before. So you have to choose your parameters such that these information set decoders or similar decoders that are exponential in size, but still they work, right? So that they cannot solve the syndrome equation. And well, the communication cost, well, of course, that's the size of all this information that you have to send back and forth. And there are some additional tricks that you can, you know, the several rounds that you have to do, you can actually compress some of the things and, you know, send a bunch of commitments in one hash instead of all separately and so on. This is, however, I mean, these are little tricks that you can do on all these types of systems. So of course we've done so as well, but I think it's not the interesting point of what we're going to do next. All right, and the communication cost, maybe that's interesting, is also the signature size when you use the Fiat-Shamir transform to create a signature from that in the end. So that's kind of what you want to keep low. One of the two things that you want to keep low, the public key and then the communication cost.
Can I ask you a question? So this vector E, the coordinates, they are not necessarily small, right? So the coordinates of E can be as large as Q.
Yes, yeah, they can be anything from Q, exactly.
Okay.
Yeah, you just have an upper bound on the number of non-zero entries in that vector.
Okay.
Well, or actually a precise number, that's that W, that weight.
Mm-hmm. Yeah.
They can be anything, doesn't matter, yeah. Mm-hmm. All right, so now our first idea was we want to replace this Hamming sphere, so this set of weight W vectors from FQ to the N, with the Lie sphere. So again, from a coding theoretic perspective, everything always starts with a Hamming metric, and classically now, and then people replace the Hamming metric with the rank metric everywhere. And now we've started saying, okay, there are still other metrics that are interesting. So we now have looked at various aspects of code-based crypto when you replace the Hamming sphere with the Lie sphere. So the Lie metric is simply another coding metric that you can use. It basically corresponds to the normal, absolute integer value, if you like, just then in a modular form, since we're over FQ and not over the integers in general. Right, so we now, I mean, that's just notation. Okay, so instead of the Hamming sphere, now I have the Lie sphere with an L up here. So I'm looking at these vectors here, and I'm not defining everything properly because we'll actually get back to, now we see the problems that arise. And we're actually then going to this restricted arrows idea, and we're going back to the Hamming weight. But that was our original idea. We wanted to go from the Hamming metric to the Lie metric. And remember that I said for these monomial matrices, if you want to replace that, you need matrices, well, you need functions, maps, that are transitive on the whole sphere, so that can, you know, map your E to any other element by the same probability of that whole set that you choose your E from. So if you want to do that for the Lie sphere, what you get is you have maps that are transitive on the whole sphere, but they are not linear. Or you have linear maps that are isometry, so they keep the weight, so they stay inside the sphere, but they're not transitive, so they don't hit the whole sphere, and actually they hit really just a very small subset of the whole sphere. And both together you don't get. So the only linear isometries, that's really what we want, are the monomial matrices that only have entries in 0 and plus minus 1. But by that, you really don't hit the whole Lie sphere. So basically you're losing too many things in either direction. Or you could translate it by saying, if we just want to use the CVE scheme as it is, but now replace everything Hamming with Lie, then you're leaking information about your secret E, namely you're leaking exactly the number of all the different values that appear in your secret E. Okay, so if your E has, you know, 5 1s and 10 zeros and 3 2s and 12 minus 1s, for example, then the attacker knows that, because that monomial matrix that hides everything, it would just be a permutation matrix, basically. So yeah, so basically you know exactly the number of different non-zero entries that you have with the exact value of that non-zero entry. And that is a lot of information. You're actually really losing a lot of security there, because you're basically saying, okay, instead of choosing from the whole Lie sphere, we're choosing just from all these vectors in that Lie sphere that have exactly that amount of 1s, 2s, 5s, minus 1s, whatever. So not good. Okay, so it's really not zero knowledge anymore. Or you're replacing the Lie sphere right in the beginning as public knowledge, but then everything is too small, and if you want to make it secure again, you get crazy parameters, and yeah, it doesn't help. Okay. But anyway, then we said, okay, but what if we do, you know, if we're sticking to these monomial matrices with only 0 and plus minus 1 entries, what can we do? Maybe we can change the whole other stuff. The type of E's that we can choose, the type of, basically that's the only thing we have to change then. And then the size of that public parity check matrix that we have to start with. So maybe we do get something better in the end. Okay. And then overall we say, okay, let's really then take the simplest of these subsets of the Lie sphere, and namely, well, so these subsets as an orbit under these matrices here, okay, because they're basically equivalent, doesn't matter which one of those you choose. So in the end, what we then said, okay, let's go with the easiest one, and just the one where also the error vector is only 0 and plus minus 1 entries. But then we have to now recompute what we can actually do if we now assume that. All right, and this is what we call a restricted error then. Okay, so because now we're saying E is not from all of FQ or ZQ to the N, it's just from this set to the N. So that's the idea of restricted errors. Okay, so, and if we go with this, let me just finish that sentence. If we go with this set here, then actually the Lie metric equals the Hamming metric again. So that's why I said we don't even have to worry about the Lie metric too much. The case we chose, then actually they are equal. Yes, so was there a question? Please.
Yeah, so basically you make the errors small now.
Yes, exactly.
In the
But the
sense
cool
that
thing,
Mohammed asked you if they are not allowed to be like large.
exactly. Yeah, exactly. So now we're restricting the choice of the error values. And the cool thing then is, of course, that, I mean, that makes attacking just finding an E randomly much easier. But the cool thing is the codes that we can now use, that property that you want, there's only a unique solution. You can now take also much smaller codes such that you have this property compared to if you don't use restricted errors, which I will show now. And that gives you smaller parameters in the end. That's kind of the main idea here.
Do we need to use a much bigger dimension and if we use this restricted errors in comparison to having uniform errors?
Smaller, we can use smaller dimensions. Well, sorry, the code has bigger dimension because we have a smaller h. Yes, exactly, yes. Yeah. That's exactly, that's really the point. So, but yeah, a little bit for the theory. I mean, so this is a little bit the outlook. This is what we choose in the end then, because that's really the easiest choice you can do. But of course, you could also say, we're taking 0 and plus minus 2, or we're taking 0 and just 3s and 5s, or 3s, 5s, and plus minus 1. You can restrict to all kinds of stuff. And so from a theory point of view, we first looked at this very general version of any restriction and showed that from a complexity class point of view, this does not make the syndrome decoding problem easier. Of course, de facto, it makes it easier because we're choosing an E from a smaller subset, so it's easier to find that E, but it's still NP hard. I mean, that's the main cool thing from a security point of view here, okay? So again, just some notation. This is now what we call the restricted sphere or restricted ball. Depends on if you want to put less than or equal here. For the security analysis, doesn't matter. So let's say this is the ball where we have a less than or equal here. So we want all the E's from FQ to the N where the Hamming weight is less than or equal to W. But now we also have this restriction that E only consists of 0 and then plus minus some value, plus minus some other value, and so on. And we take little a of them. Okay, for our application later on, this will just be plus minus 1. Right, but for the very general version, we show that then this restricted syndrome decoding problem, we call it. So again, you're given a parity check matrix, you're given a syndrome, and this weight W, and of course also these numbers here, so the restriction parameters. Then the syndrome decoding problem, the decisional version is, well, given all of that, decide whether there exists such an E in that set, in that restricted set, such that it's a solution to the syndrome equation. Okay. And then, of course, the computational version of finding that E is always harder than the decisional version, but the decisional version already is NP complete. And the hardness comes from a reduction from the classical syndrome decoding problem. By some Kronecker product, you can basically say, okay, if we have the classical problem, we can expand the whole thing into a longer code with the Kronecker product and expand the errors that we have into a longer error that only has smaller values here by some function that we define. And then you can show, okay, so if you could solve the restricted syndrome decoding problem, you could also solve the classical syndrome decoding problem. And since we know that the classical one is NP hard, also the restricted one is NP hard. And that they're in NP is also easy to see, so it's NP complete. All right, so of course, I mean, the proof is a little bit more involved. If you're interested in that, I mean, we can talk about it later, or you can have a look at the paper, of course, if you like.
Okay, I've got some questions.
Sure. Yes.
Yeah. So this reduction, I'm interested to know about the parameters being involved here. So if you take, for example, one standard SDP, which has Q, P, M, and W. What are the parameters of RSDP? So can you work with the same Q, same P, same M, same N?
Yes, so the Q stays the same. The N becomes longer depending on this A here. Because what you're basically doing is, okay, you're taking your classical SDP with error vectors from FQ to the N with no restriction. And then you're saying, I can find some other set, call it U or whatever, such that this has, well, some other numbers, little u maybe, number of elements such that u has an element such that u times any number in this restriction set gives us all of fq. So basically what you're saying then is, okay, I'm now expanding my original code and error vector of length n over fq into something that lives over this restricted thing, but not over fq, over the restriction, not fq over the restriction, not of length n anymore, but length n times that cardinality of this set u that you need. So, and that cardinality of set u depends really on the choice of these values here.
Yeah. Okay.
It's at most q. Or it's
Yeah,
at most
definitely.
One.
Yeah.
If you take just plus minus 1 here, it's q minus 1/2. So you get a code that is q minus 1/2 times as long as the one from before.
Yeah. Okay. So it's okay. Okay.
Yeah.
It might be. Is it related to log A somehow? No. A or log A? Because I'm thinking information theoretically. Because the entropy that you have the other way has to be enough to match that you said that.
Yeah, absolutely, exactly. Could be. Didn't matter for us because for the NP completeness proof, it doesn't matter because it's still just a scalar factor.
It would probably matter later if you want to choose your parameters based on S.
Yeah, that's right. But then this translation into the syndrome decoding problem is worse than what we actually do in our analysis.
Yeah. Okay, so there are still yet more still to come.
Yeah, that's right. But I think let me just check the times. Yeah, I'm running out of time very quickly, but it doesn't matter. It's always nice to discuss more details of what I have. So
yeah,
that's good. So now let's just restrict to what I said in the beginning. So that was the general thing. Okay, so basically we're just saying restricting the error values makes the whole syndrome decoding still NP complete. And now, I mean, of course, now you have a wide variety of what you could do with that. For us, we now restrict to this restriction that we still live in FQ, but we want to just have error vectors with 0 and plus minus 1. And what do we do then? So maybe I'm just shortening everything a little bit here, although I find this is the most interesting part because that's where my coding theory expertise comes in. So basically, we're just now setting up the whole coding theory, all the classical things with minimum distance, error correction capability, Gilbert-Vashamov bound for this new setting. Okay, this is well, something that hasn't been studied before as far as we know. So this is what we do here. Okay, so we want to have error vectors with just 0 and plus minus 1. Now, however, the little trick is, okay, now you have to think about what is the possible set of vectors that you can get if you take 2 error vectors and take a sum or a difference of the 2. And what you could get then is still zeros and ones, and plus minus ones, but you could also get plus minus 2 entries in a sum or a difference of 2 error vectors from this restricted set. And then you have to set up a restricted minimum distance or restricted weight to, well, that's what you need for the coding theoretic purposes. Then I'll show you on the next slide. So we define the restricted weight for our purpose now as, basically now we're back to the Lie weight. If you know the Lie weights, the Lie weight of any vector that lives in, well, that just has entries from 0, plus minus 1, plus minus 2. And we call the weight, well, or we say it's infinity if our vector has any other entry, okay, if it's not in that restricted set. But now the restricted set allows plus minus 2, okay, that's the little difference to before. And well, the restricted minimum distance is just analog to to classical coding theory, it's that restricted weight of all the elements of our code. Okay, so it's the minimum of the restricted weights without the zero, such that, you know, like C is in the code and then, well, it's not in zero, but it's in these guys. Okay, and anyway, if if C doesn't have any element, so C is our code, right? If C doesn't have any element with just 0, plus, minus 1, plus, minus 2, then we set, except for the zero vector is always in a linear code, then the minimum distance of the whole code is infinity again. All right, and now the cool thing is, what can we do with that? So if we have a code with restricted minimum distance d tilde, then for any parity check matrix for that code and for all values w that are less than half of that d tilde, there cannot exist two distinct solutions to the syndrome equation. All right, so there, the other way around, there's a unique solution to the syndrome equation. And maybe just a little proof here, because then it shows where this plus minus 2 comes in. So remember that E is only in plus minus 1 and 0 to the n. There's a to the n missing. So if we had two different solutions to the syndrome equation, then we can also say, okay, E minus E prime times H is equal to 0, meaning it's a code word because it's a linear code. Then we do know that E minus E prime has only 0, plus minus 1, and now plus minus 2 entries. And it has restricted weight less than d tilde. That comes from starting assumption that both E and E prime have this restricted weight less than d tilde half. And again, you can think about it coordinate-wise, you cannot get to twice of that. Then, hence, since our code has restricted weight d tilde, it must be that E minus E prime is equal to the 0 vector, and hence E is equal to E prime. So that's, I mean, that's kind of, you know, of course, when you start thinking about it, you go backwards, right? You start with this, and then you say, oh, this is actually what we need here. And then you define the weight accordingly. And of course, you could do that for any other values too. It doesn't have to be this restriction, but this is simply the simplest. And now there's a little catch here. Of course, you need your field to have plus minus 1 and plus minus 2, which you only have if your characteristic is at least 5. However, if your characteristic is 3, what happens then? Well, these guys are also equal to plus minus 1. All right, so your E minus E prime lives in F3 and not in this thing, but you know, you have a similar result. Alrighty. Then we have the Gilbert-Vashamov bound. So the Gilbert-Vashamov bound, the idea was, if I give you, so if you reformulate it, if I give you a random code with a given dimension and a given length, what is the most likely the minimum distance? And we do the same here with a restricted minimum distance. So if you, I mean, this is the original version. Usually you formulate it in terms of what's the dimension if you fix a distance, but then you can, of course, kind of turn it around. So this is the important part that we need. So we define the Gilbert-Vashamov distance for a code as, okay, it's the maximal d tilde such that the volume, this is the volume of the balls of length n with a given restricted minimum distance d tilde. Such that you have this equation, and this is exactly what comes from up here, all right? And if that is not fulfilled for any valid d tilde, then we simply again say that minimum the restricted Gilbert-Vashamov distance is infinity, and it is not fulfilled if you translate that as soon as the volume of, you know, length n and minimum restricted distance or Lie distance to n, that's the most you could ever get. And if that is less than q to the n minus k minus 1, your code has no element in 0, plus minus 1, plus minus 2 to the n. Okay. So one more thing here, then you can, you know, get a probability estimate on saying, okay, what do we need to have fulfilled such that our code has a minimum distance infinity? And I have to go a bit quicker and not go through the details, but it's really, I mean, that's just math, you know, equations left, right here, plus, minus a little bit of there. So this is what you get. So the cool thing is whenever you have a random code where your dimension of the code is less than or equal to this thing here, for any epsilon, all right, we can uniquely decode any E from this restricted set. Because we have minimum distance infinity. Minimum distance infinity means every vector that we're looking at has, well, minimum restricted distance less than infinity. So everything is uniquely decodable from a syndrome equation. That's the important point here. Of course, this is a little bit of a restriction. Okay, we have to live with that. And the other thing is that we need Q greater than 5. All right, so, but okay, we can live with that as well. But that's, all right, so that's the Gilbert-Varshamov bound. Yeah, let me just show you very quickly. Then we basically just replaced in the original CVE scheme. Now we replaced this Hamming sphere that we had here before with these restricted errors now. We replace these monomial matrices with any scalar factor from before. Now we replace it by only 0, plus, minus 1 entries in those monomial matrices. And the only thing that we change down here is, well, we have to accept, not before it was the weight, the Hamming weight of E is equal to W. Now we have to say, okay, E prime is really from this restricted set that we want. Everything else stays the same. Oopsie. So also really the whole security analysis stays the same. Completeness, zero knowledge, soundness, cheating probability, even that more or less stays the same. So we're still at 1/2 for large P, and then to get cheating probability at most 2 to the minus T, you need approximately T rounds. That's kind of important. Okay, that you need as many rounds as your security level should be. We have an average communication cost, a maximal communication cost. The only difference is these guys here. All right. And then we have to look at these generic decoders. How hard is it to find the E from SNH? And again, we look at ISD decoders that do not make much sense in the setting that we looked at. Then we looked at generalized birthday decoders that are the most efficient. And really in that case where we are, so something called Wagner's algorithm is a standard thingy there. It's really the same as a subset sum solver, because now with the plus minus 1 restriction that we have, it's really the same. Maybe you need to think about it once, but it's really the same as a multi-dimensional subset sum problem in the end. So let me just skip that. This is that partial Gaussian elimination, birthday decoding with Wagner. Okay, so I mean, we adapted everything that's already known to our setting. Okay, so of course you have to change a few things with these restricted errors now, and then do the whole complexity analysis, which we have done. And this is the very wonderful formula. Okay. And then of course you can get the parameters from that. So let's see what we get. For security parameter 87, I never liked, but that comes from other papers that have done so before. Cheating probability 2 to the minus 16. Seeds and hashes, okay, again, standard things that, you know, you don't have to send the whole matrix that you randomly chose. It's enough if you take the seed of the pseudo-random function that you use for that, and so on. So anyway, so we use seeds and hash functions of these sizes. This is now, okay, this goes back to your question, I mean, from before. This is now the length of a code and the dimension that we use here. So the size of H is n minus k, so pretty small, times n. The field size is 29. Yeah, n is 167, also that is actually pretty small still. Number of rounds is 17, as I said, about the security level, that cheating probability level that you want to have here. Public key size now for us is this. For the original CVE, it's 512. And for AGS, that's simply another zero knowledge code-based identification scheme, just for comparison, a lot larger than what we do. All right, but even the CVE original scheme is really quite a lot larger than what we do. So that's nice. We're really restricting the public key size a lot here. And the communication cost, so on average, we are a little bit faster than these two guys. For maximal cost, we are even better compared to them, but I mean, the average is what we're really interested in. So we are a little bit better here, but now comes my little disclaimer that I had to add here. So we're currently recomputing the parameters, but we're not quite done yet, unfortunately. Otherwise, I would have added them, of course, because there's a new subset sum solver that we now have to adapt. These parameters were computed before that new paper came out. So we're getting a little bit worse here. However, we're still smaller than these guys here, but we're not quite sure where in between the true parameters should be now. However, the public key size still stays in that order here. All right, so that's cool. I mean, we're winning in both cases, so that's nice. So this is compared to the other zero knowledge identification schemes. So that's nice. And now let's see what it does for signature.
Can I ask you a question?
Of course.
So these sizes, so for example, for the average communication, does this mean 2000 kilobytes or 2.3 kilobytes?
2.3.
Ah, okay.
Yeah. That's
also
yeah.
for this parameter, I couldn't quite understand the relation between the security parameter and this cheating probability.
Okay, so the cheating probability is really just this, yeah, okay, so the security parameter is basically for anything else. So how hard would it be to find the secret? Okay, there's a difference between an impersonator being able to be accepted. That is basically the cheating probability. The security parameter, because that's really from a security point of view, the more drastic thing is if you could really recover the secret. Yeah, so that's the difference here. For the signature scheme, they have to be equal. For if you're just looking identification parameters, they don't have to be equal. If you want to make a signature out of it, they have to be equal.
Okay.
Yep. So that's what we do now. So for if we want to make a signature scheme out of that, we set the security level to be 128 bits, and then also the cheating probability to be to the minus 128. Then the number of rounds again is approximately 128. For us, it's de facto a slightly bit more, but again, that doesn't matter much. So the code size that we need now, oh, sorry, of course, now we need seeds and hashes of twice the size of that. The code size also kind of by chance is the same length, 256. K is 204, so again, H is approximately 50 by 256 bits. Sorry, FQ, so F31 elements. So times log P if you want to think in bits. So this is what we get. So it's 260 bits. Whereas in AGS, you need 1,500, CVE, you need 800 and a little bit. So again, quite a reduction in what we do here. The average size, signature size is 43 kilobyte. Here we have 41, and we are down to 30. And again, with the disclaimer, it's probably a bit larger now that we have to recompute everything. It will be somewhere between 30 and 40. And the maximum size will also be somewhere between 30 and 40. That actually in our case never changes, whereas for CVE and AGS, the maximum signature size becomes significantly larger again. So again, our large selling point is compared to the other code-based schemes, in particular reduce the public key size. And we also reduce the signature size. However, as I said, we have to check a little bit by how much really. I think it's still quite significant, but we really have to do the computations before I can do that in written somewhere. And of course, now it's interesting to compare it to other signature schemes, so non-code based ones. So again, let's just recall what we have here, 128 bits security level. So that's more or less the same everywhere where I compare. Public key size is only 260 bits. That's just, okay. And signature size, roughly 30 kilobyte. Then we have one, okay, here is another code-based one based on rank metrics. Public key size, a lot larger than ours, so 1200 bits. Average signature size, 22 kilobytes. So that's lower than ours compared to others in the same range, I would say. Then there's Durandal, public key size a lot larger than our signature size, a lot smaller. So really that's a very asymmetric thing that you have here. Then there's less security, same level, public key size and signature size 15 kilobyte. So that's kind of the opposite of Durandal. Okay, this is very symmetric. And so public key size a lot larger than ours, however, signature size smaller. And then there's Wave. Public key size 3 megabyte, Okay, a lot larger now, signature size, 1.6 kilobytes. So that's really a small signature here. So, well, path minimizes the public key size, and it really depends on your, on your application, what you want. If that's really your goal, then our solution is a good alternative. If, of course, you want to minimize your signature size, I mean, then our 30 kilobyte cannot compare with any of these guys down here. All right, so that's just my summary and conclusion. So basically what we did was we took the classical synonym decoding problem and the identification scheme that there is, and we replaced that coding theoretic idea from taking Hamming metric codes and Hamming decoding algorithms in there and replace it by this restricted errors idea. And then we did the whole coding theory and the whole generalized decoding, generalized birthday attack decoding there. And we got parameters that show that even though the problem seems a little bit easier because we're restricting the error vectors where they come from, you can choose other codes and hence even more reduce the public key size than what the other code-based systems could already do. And you can do that for a general identification scheme or with the Fiat-Chemie transform for digital signatures. And another thing that is again cool, because we only have ±1 multiplications in everything that we do, because of our restriction, the implementation is also very fast because you don't need any, basically no finite field operations. Yeah, you're only in F2 still, or F3, let's say, plus minus. So that's another cool thing about what we do. So that was, I know the second half very brief, but it was nice that we discussed about more details in the beginning. So yeah, I still have time for more questions and comments, and otherwise, thank you for your interest.
Thank you very much, Lena. I want to ask you about how did the public key size is reduced, because so the public key is this S and H, right?
Yeah.
So is H more structured in your case in comparison to CVE?
No, it's just that we can use larger codes, as you said in the beginning, we can use larger codes and hence the parity check matrix becomes smaller. Like larger in sense of dimension. Sorry, so let's say for the same field size and the same length of the code, we can now use a larger K and hence a smaller parity check matrix, because that restricted minimum distance will be larger than the classical Hamming distance, and hence we can allow a smaller code and still have the unique error correction capability.
Okay. Yeah. Okay.
That's really the coding theoretic idea behind it.
Yeah. Okay. So you can basically satisfy this unit decoding property with smaller parameters, right?
Yeah.
Okay. Any other questions? I mean, do you have a question?
I've got one, or maybe more. So was there any particular reason you did it on this CVE style idea schemes, or show it at least here, or you have done also the Fiat-Chemie ones and you know it's working well? And
I mean, Fiat-Chemie is just the transform, or what do you
mean? Yeah. So have you done that Fiat-Chemie itself, or no?
You mean implemented, or what do you mean?
Yeah.
Like as a real signature scheme?
Real implementation, yeah.
No. That is actually one of, on the list of things to do, but we're still, at the moment, we're still struggling with the theory and reviewers that come up with new things that could be a problem.
Okay.
No, which is nice, right? But that's always the problem. If you're trying to set up a crypto system, it takes a while. It's really a lot of work to have thought of everything that could possibly happen.
Okay. And
much easier to break stuff, right? So anyway, no, we haven't implemented it yet, but I mean, theoretically, I can tell you exactly how the Fiat-Chemie transform would work with it. I mean, you just need an oracle for it.
Yeah.
Instead of the verifier. But but we have no implementation yet, but it would be nice to have. I totally agree. And it's on the list of things to do, but I feel that it could still take a while.
Okay.
And sorry, and the other question was, why did we choose CVE? Because there are others like Stern and AGS itself and so on. CVE is first of all defined over FQ, so that's what we needed. Other things that are defined over F2. So for example, there's an F2 version where you only need 3 rounds instead of 5 communication rounds, like rounds, but communication steps per round.
Yeah.
But F2 didn't help us, so we really need that FQ version. And so CVE does that, but others do that too. But CVE is just kind of nice and simple, and like that AGS one is just more complicated to understand, and it doesn't gain anything. So that was the choice for CVE.
Yeah. And probably one last question, going beyond F2 to FQ, I noticed that you only work with the prime fields, right? F19 and F30,
For the final
F29 and
parameters.
31. Does that M in the power will help you at all? Like instead of having FP, you use FP to the M.
So that's another general thing that most code-based cryptographers say. If you work over extension fields, non-prime fields, you always have the problem of some subfield attacks and things like that. And it didn't gain anything for us in parameters. Like,
yeah, okay.
You know, I mean, we plugged it in, and I mean, you can do it, sure. But then we just said, okay, since we don't win anything, we just have more risks that there are subfield problems there. Actually, we even know like how you could use some of that. So we just said, no, I mean, there's no point in doing it. So let's just go with prime fields and not have subfield attacks here. Yeah. But yeah, that's really a classical thing, I feel. Maybe, you know, anyone can correct me, of course, but it's a classical thing that in crypto.
Yeah, well, that's a classical question in coding theory and a classical answer in cryptography.
Yeah. Yeah.
And everywhere in this kind of parameter setup, you have chose A to be that A parameter that you had to be 2, right?
No, so A is equal to 1 because in our proof for the NP completeness, we always needed something that we call a symmetric restriction. So you always need, if you have 1 in there, you also need -1 in there, like that the math works. If you add, you know, another value, you also need the minus value. So A was the number of +-1 values that we allow. And
yeah,
since here we only allow +-1.
Yeah, but the unique decodability was working with +-1 and +-2, right?
Yeah. But E is still, so the restriction is still.
Oh, yeah. That was the difference of E's there.
Yeah, exactly. And
okay.
then, so that's also a general thing. If you're now allowing +-1, +-2, you need to define the restricted weight for up to +-4, because you just need to look at the set that the sums and differences of all.
And did you try that one as well?
No. We just
in the interest of getting better sizes.
There's no point. Like, let's just not spend our time on that. But as I still think there could be something out there that the +-1 restriction is not necessarily the best. It, like, by a very strong feeling it is, but it's just a feeling. But we haven't done the whole math for the other things because the paper is pretty long already. Like, I mean, the talk of course shortens everything that we do, but yeah, it's definitely worth trying other parameters, sure. But again, we haven't done the whole math for other things. We've restricted to that, and we're quite happy with what we got.
Okay.
Yeah.
Yeah, I don't have any other questions.
Yeah, I think in the interest of time, we may conclude the session here. Thank you very much, Lena, again, for your interesting talk. And thank you everyone for tuning in. And hope to see you in the next seminar.
Yeah.
See you everyone.
Yeah, thank you.
Bye everyone.